Okay, so in this example, we're going to try to estimate the square root of 1 plus x using this Taylor polynomial. And notice, since it's just a line, this is just a first order Taylor polynomial. It's just your tangent line. And we're going to try to approximate that for values of x such that the absolute value is less than 0.01. So the first way I'm going to show you how to do this is using Taylor's remainder theorem. So that's mathematically going to give us a bound. And then at the end, we'll also look at the same idea through a graph, and we'll actually graph the two functions and then graph their error and compare that with what we got. So first, I need to figure out where this Taylor polynomial is centered. So what was the a that we used to come up with this Taylor polynomial? And and I'm going to also have you just put this on pause if you haven't already and try this problem first on your own and then turn it back on to check your answer. Okay, so a reasonable guess for A is that it's probably going to be 0 because our interval where we're trying to use this estimation is centered around 0. But we'll just do a quick check and make sure that if we found the Taylor polynomial, we're going to try to find P sub 1. And we're going to assume that it's centered around 0. So I'm going to have f of 0 plus f prime of 0 times x minus 0 to the first. So those are just my first two terms of the Taylor series. And I'm just going to check that if I do this that I get 1 plus x over 2 back. Because if not, then I would know that my a is a different value where I'm centering my Taylor polynomial. Okay, so just like we did in class, so we're going to fill out this table here. We only need two terms. We're just going to start with the function itself, and then we're going to take one derivative, 1/2, and then we'll evaluate both at 0, in which case I would get 1 here, and I would just get 1/2 here. So if we plug those back in to these pieces here, we're going to see that we do in fact get back to this line that we started with up here. So we know that we used a first order Taylor polynomial in this approximation. So how bad is our error? So if you recall, anytime we're going to use a Taylor polynomial to approximate something, that I can write the function is equal to the Taylor polynomial plus some error, which is really our remainder term here. And if you recall, r sub 1, your remainder, we'll do the absolute value here. We're going to put a nice bound on this. This is going to be the next order derivative, so this will be the second derivative, evaluated at some c in between x and 0, over 2 factorial times x minus a, which in this case is 0, squared. Okay, so that is a bound on my error. And again, so c in this case is between x and 0. So because I'm going to need the second derivative, let's actually fill out this table for one more step. So with the second derivative, I will get this. So now what we're going to do is just try to bound this. I want to figure out what is my worst case scenario that this will be on my interval where the absolute value of x is less than 0.01. And before we move on, I just want to point out that these first few terms that we found are actually the first few terms of a special type of series. So anytime you have a function of the form 1 plus x to the p, where p is any real number, then we can write this as an infinite series that's called a binomial series. And we can show that the binomial series will always converge as long as the absolute value of x is less than 1. So we'll look at that more in class, but I just wanted to point out that this is a special case of the first few terms of a binomial series when p is 1/2. Okay, so just summarizing a few things we found on the previous page. Now we're just going to look at how we can bound this. So if I replace the second derivative here with 1/4 and then I'll put this in the denominator, and then I have c here. And then we will also multiply by the 2 factorial out here. And then in the numerator I will still have x squared. Now I want to figure out what's the largest, what's the upper bound I can put on this. So we know that since the biggest that x can be is 0.01, that will give us a good bound for the numerator. And I can get rid of the absolute value, or the negative sign inside the absolute value. So I'm just going to have 0.01 squared here. The denominator, I know I'm going to have 8, and then I need to figure out what's the worst case scenario that this can be. And recall, c has to be somewhere between 0, because that's where we're centering this Taylor polynomial, and x. And we know x is between negative 0.01 and 0.01. So in order to make this denominator smallest, I want to figure out what will make the denominator term smallest, because that will make my overall fraction biggest. And so notice this term inside here will be smallest if I let c be negative 0.01, in which case inside here I will now have 0.99 to the 3/2. Okay, that's how I'm going to get this whole thing to be the biggest that it will possibly be on this interval. So we're going to let c be negative 0.01. That will get us the smallest denominator that we can get in this scenario, which will give us the overall biggest bound on our error. And then notice if we plug this into a calculator, this is going to be approximately 1.27 times 10 to the negative 5th. So that's giving us a good bound on how far off we will be if we approximate this actual function with its tangent line. So now let's look at this with a graph, just so we can picture what we just found. Okay, here's just a summary of what we found for the error. So now let's plot both the original function and its first order Taylor polynomial, or the tangent line. Okay, so here is a graph of both the original function and then the tangent line approximation, which is the first order Taylor polynomial. And we notice that we're really only going to use this approximation where x is very, very small. So we'd have to zoom in to a tiny little region. That's not even small enough. I can't draw it small enough on here. But we want to see when x is just between 0.01 and negative 0.01, how far off is our error. So really in terms of the graph, that's just saying, like, if you're going to subtract those two functions from one another, what's their difference? And you can't tell visually looking just at this graph, but we can actually graph the error function. So let's take the difference between the two functions. I'm going to take the blue one minus the red one, and we'll plot that next. Okay, and I also just zoomed in. If you look now, my x-axis is actually only going out between, in the interval we're interested in, between negative 0.01 and 0.01. And so then you notice, looking at your y-axis, that the max y we get there is actually just over 1.2 times 10 to the negative 5th, which is exactly what we predicted. We predicted that our maximum error is going to be less than 1.27. So again, we got an upper bound on the error. We kind of got the worst case scenario, and we can see that the error changes depending on which x value you choose. But as we get a little bit further out on the interval, as we get closer to 0.01 or negative 0.01, that's when you can see our error up here is approaching 1.2 times the negative, or times 10 to the negative 5th. So that's just another way of viewing what we just found mathematically. And that's it.